Almost 2 years ago, I uploaded this video where I remade my old project with Bevy and Rust. In that video, I was able to successfully manipulate the 2 million pixels on my screen to resemble 2 alien armies having a go at it. At the time, I was very satisfied with what I achieved. This was a video which I actually believed deserved the clout that it was receiving, but I've grown as a programmer since then. I've grown as a channel, and I've even grown as a person. The point is that I'm no longer satisfied with that video, and this new version of the project will be more performant, elegant, and glamorous than the older one. It also won't have a train wreck of a code base. Anyways, let's hop into the video. So a quick note, about a quarter of the way through editing this video, I accidentally deleted the repository with a GitHub command, so the video understandably doesn't flow in a very linear way. I basically rewrote the whole project with the performant features immediately instead of evolving the project like I would have done without deleting the repo. Consequently, I don't have the recordings for the time that I spent building the project, but I do still have some footage from the old project when I first started working on it, so let's actually hop into the video now. Feel free to skip around the video using timestamps because a lot of the technical details are at the end of this video and the beginning might be a little boring for you experienced programmers. So right off the bat, I was able to move the units around and draw a smiley face with the targeting circles. This is a very old version of Bevy first off, so at the time I got started on updating the versions of Bevy and all the external dependencies which I relied on. After this, I took a look at the code and I'm not exaggerating when I tell you that this was one of the most messy and inefficient pieces of code that I had seen in a while. So of course, the only way to rebuild code is to destroy it, and thus I got started on simplifying the project to its base function. I removed every feature except the ability to collide and move units around. You might immediately recognize the inefficiency of my collision system. Let's turn up the amount of units, and if you didn't notice, this project runs at an abysmal 1 FPS. Let me explain why this happens. Right now, the runtime complexity for our collision algorithm can be denoted as ON squared, which is to say our game will run exponentially slower the more units we have. This is because we are checking collisions for every unit with every other unit in the game. For example, this unit in the top left still has to check if it is colliding with this unit in the bottom right. To fix this problem, I'm going to be using something called a quadtree, which some of you might recall I failed to implement in the previous video. While I was definitely able to implement a quadtree successfully, soon afterwards, I ended up running a GitHub command and passing in the wrong parameter, accidentally deleting my entire project. So from this point on, the project that you see on screen is recorded on a newly built version of the game. So as it's probably evident, I made a lot of changes off camera. Let's start off by listing the changes I made before going back to talking about quadtrees. First off, I'm very conscious of the fact that games like these need accurate collision even at low FPS, so I made all of my systems run on a fixed update. Of course, we implemented a quadtree, but also a rendering optimization called shader instancing, which I will go into later in the video. But back to quadtrees. The basic idea of a quadtree is that it's subdivides based on the amount of units in a sector. This allows us to create a robust spatial partitioning system that is a lot more advanced than a basic grid. As you can see, the units only check for collisions with other units that are in the same node. This FPS is a little higher than what it would normally be because I also had shader instancing implemented in this clip, which again I will explain later in the video, but the quadtree improved the performance a lot as well. Although I decided to use quadtrees in this game, it is not always the best option. In some cases, a basic grid is the better option for a game, but since I've chosen to add a quadtree to my game, I'll start off by defending my use of it and talk about the advantages of a quadtree over grids. Quadtrees are usually more efficient in memory as the amount of cells dynamically increases to account for the actual amount of objects on the map. We do lose some benefits of grids, such as the much needed simplicity in a genre often very complicated to program. The ability to use, for example, line algorithms or circle drawing algorithms to access cells in the grid are lost. Grids also offer a surefire and easy way to access neighboring cells and are much easier to navigate than a quadtree. I've chosen to implement the quadtrees using recursive structures, so it's also going to be a lot more difficult to navigate. You might notice that I've replaced the old model with some cube meshes. I've noticed that Bevy has spent quite a lot of time on rendering my units, so I've decided to work on something called shader instancing. Now before I go ahead and explain shader instancing, I'm going to make a 3D model for our units, and I think it's fitting to explain shader instancing over a time lapse of me making a 3D model because the basic idea of shader instancing is to redraw the same mesh multiple times in order to achieve a drastic performance increase when drawing the same units several times. In my case, shader instancing is a fantastic optimization due to the several thousand units which pretty much share the same mesh in my game. One of the downsides of this method is that I forgo all traditional methods of bone animation. For now, we're going to ignore this problem and use static meshes for our units. Bone animation is in itself a pretty costly operation, so perhaps it is for the best if we don't have this many units performing that operation anyway. To actually perform instancing, we need to write a custom shader which renders our units and runs it through a rendering pipeline separate from Bevy's built-in rendering system. Instead of creating separate entities with PBR bundles for our units, we will just have one entity with an array containing data for each instance of the mesh we need to draw. This data will be modified every frame in order to draw our units. We can still use entities for our units, but these entities will not contain a mesh and have purely transform and unit marker components. At the end of each frame, we will take the position, rotation, and other useful information from these entities and feed them into our instance data component, which will be read and drawn by our rendering pipeline. Anyway, since I've explained the instancing process, let's actually draw a mesh instead of a cube. So the 3D model that I made earlier looks okay from afar, but if we take a look at its topology, you will notice that there are many unnecessary vertices and a lot of unnecessary details that won't be needed when looking at them from afar. This will probably cause our frame rate to dip a little, but I decided to keep it because it's too much of a hassle to change at this point. I decided to make our units tanks because this would create the illusion of a more large scale battle, which is kind of what I'm looking for, and it also looks relatively good even without any advanced sort of animation. I'll add other units later in the game, but for now we can just use tanks. Another fact is that making all the units in this game into machines would be a good way to compensate for the fact that any performant type of animation with instancing would require lots of hacky coding that I don't think I'm ready to mess with yet. But another fact is that at the moment our units can't rotate due to my limited instancing system. Again, since I rewrote my project after the purge so quickly, the recording you see on screen right now is actually not limited and the units can in fact rotate, but I made them not rotate for the sake of progress. But our custom pipeline does not support rotation, so that's the first priority implementation which we need to get started on. While implementing rotation in my instancing system, I decided to create smooth rotation for our units and add a custom slider that adjusts the rotation rate of my units depending on their unit type to give some realism to in the game. The tanks now sort of seem like actual tanks, turning at a slow rate to simulate what an actual tank would probably look like. I don't think this ended up actually helping, but it does make the game look a little bit polished, so I'm fine with it. Remember when we removed the ability to attack in the game? That's pretty much the entire point of an army, so since most of our systems are basically done, now is the time to add that ability back. But with the addition of our spatial partitioning system, it's actually a lot more complicated. Whenever we need to check for nearby units in our game, it's hard to decide what cells to check due to the dynamically allocated size and location of the nodes in our quad tree. If we were to check all the units in our current node for nearby enemies, this would yield invalid decisions and would not work. The results from checking only our current node would not allow us to have long range units and oftentimes makes us blind to units in the neighboring grids which would otherwise be in range. The reason we can use this for collision is because it doesn't need to be as accurate as detecting an enemy has to be. This is because humans generally cannot notice when collisions are calculated slightly incorrectly, but they will definitely notice if two units standing next to each other do not attack. So before we add attacking to the game, let's first implement a way to get the nearby units that we will check if we are in range for. Now while I explain to you how I'm going to do that, I'll play the final result of my efforts because the simulation does take quite a while to finish and this is a pretty good part to fit it in considering what I'm about to talk about is long and probably boring to a vast majority of you. The first most obvious and also low effort solution is to make the minimum grid size of the quad tree larger. We can accomplish this by decreasing the maximum level of subdivision so that the nodes will become bigger even when subdivided. This solution is simple to implement but it does present a lot of other problems as well. Let's say a unit is on the edge of a node. This unit is completely blind to, for example, a unit which is 1 meter away from it but has been partitioned to the node right next to it. Let's shelve this solution for now because although it might seem usable, it is very inaccurate and I don't like to keep hacky solutions in my project. It also might decrease the performance of our project because small grids are required when there are a large amount of units. Another solution is to create a way to check all of the neighboring cells in a grid or cells that are just in range. Now the way I made this statement leaves it very open for interpretation. How exactly are we going to to find the nodes that are in range. So as is immediately evident, the one con of this solution is that it is very complicated and difficult to implement, and can also be very costly on our processing power. But after stressing about it for several days, I actually thought up an algorithm which can help us find neighboring grids relatively painless. So my idea is to begin on the parent node. If the bounds of the child nodes are close enough to matter to the unit or contain the unit itself, we call this function again on the child nodes. We can keep repeating this process until we reach the very bottom of the quad tree. At this point, we have every child node which is in range of our unit, and we can add the units in these nodes to our list. I had to completely overhaul my quad tree implementation for this solution, as previously I was storing units that were not completely inside a node on the parent node of that node, and this would help collision become more accurate, but now I had to change that to make every unit at the very bottom level of the quad tree by making them points instead of units with size. This vastly changed the way that I calculated collisions in order to determine this solution, as I didn't want to check two different lists of units for collision and enemy detection. I'm really glad I did it because these new units move in a much more organized way. It doesn't seem as satisfying as the chaotic bumping of units that we previously had, and it is slightly less performant, but sacrifices need to be made in order to turn what would be a tech demo into a working game. Final note is that I also removed the smooth rotation because the game seemed unresponsive with it in the game. So after that, as you can probably tell by the last 5 minutes of the video, I actually added attacking to the game. It was really simple but kind of tedious. I'm going to cut the video here because it is getting quite long. I really don't want to be going above 13 minutes with this video, so subscribe and like if you made it this far into the video, and maybe I'll make a new video where I add things like textures, more than one type of unit, animations maybe, terrain, better shading, and a load of other things that this video did not cover. Now, I made this video mostly to just document different techniques of optimization that I used to make this many units on screen possible, so have a good day, and I hope to see you again in the next video.